The formula Q equals C delta T for calculating relating heat and the change in temperature is applicable only if no phase change and no chemical change is occurring in your system. Okay, in fact, temperature could change in a system during a reaction with no heat exchange between system and surroundings. So you can have a change in temperature, but Q is zero. We'll talk more about this when we get to the lesson on thermochemistry. Now, heat could also flow in or out without a change in temperature during a phase change. So in this section of the lesson, we're going to focus on phase changes. There are phase changes that are endothermic. These are the ones that involve a flow of heat into the system, even at constant temperature and at constant pressure. So for example, the melting of a solid to a liquid at constant temperature and pressure is an endothermic process. Okay, so water, for example, can turn from ice to liquid at 0 degrees Celsius at 1 atmosphere pressure. And for that to happen, heat has to flow in from the surroundings. The amount of heat involved there is called the heat of fusion, which is symbolized by this thing right here, delta H with an FUS, which is an abbreviation for fusion in between. So the heat involved in melting is called the heat of fusion, or you can put the FUS subscript after the H. Okay. Now, solid to gas is also an endothermic process. That the amount of heat involved there is called the heat of sublimation. And from liquid to gas, changing from liquid to gas, that's evaporation or vaporization. The heat involved there is called the heat of vaporization, or delta H vap. And for sublimation, it's delta H sub. Okay. Now, these are numbers that you can look up. But the numbers you will look up was usually given per gram or per mole. So make sure when you're doing calculations that whatever values you look up for these things, you have to multiply them by the actual mass if the value you looked up is per gram, or by the number of moles if the value you looked up is per mole. Okay. Now, the opposite of those phase changes would be exothermic. So, for example, we said that solid to liquid is endothermic, right? Delta H is called delta H fusion. Well, the opposite, going from liquid to solid, okay? So liquid to solid right here would just have the negative of the delta H of fusion. So it's going to be the same value except it's negative. So it would be an exothermic process. So when liquid water freezes, it is an exothermic process. It generates heat. One experimental observation that demonstrates this, if you were to cool, for example, so if you were to plot the temperature versus time, you put a test tube filled with water, okay, for example, and you put it in a very cold environment. So like you can have like an ice and salt mixture here. So this is below 0 degrees Celsius. Okay, if you monitor the temperature of that, it's going to be dropping quickly. But once the ice starts melting, what's going to happen is the rate of cooling is going to slow down. In fact, it gets arrested. Okay, this flattening of the curve, temperature versus time curve, is indicative of a liquid turning into a solid. So why does this flatten out? The reason for that is as the liquid is converting into a solid, it's releasing heat. So the temperature won't go down as fast as you would expect if it wasn't generating heat. Okay, so and then after everything's frozen, that's the only time when your temperature starts to drop again. Okay, so this is the way you would determine the freezing point of a liquid. This is called a cooling curve. Okay. Condensation, the same thing. That's the opposite of vaporization. So conversion of gas to liquid, the delta H for that is the negative of the delta H vaporization. So you can't look up delta H for condensation, just look up delta H for vaporization. The negative of that number will be the delta H for the condensation. Similarly, if you have a gas turning into a solid, the amount of heat involved there is just the negative of the heat of sublimation. Okay, so let's That's a couple of questions here dealing with that concept. A person with a fever, 38 degrees Celsius, normal body temperature is around 37. So let's say you have a person with a fever, you give him an alcohol rub, and the reason you do that is to make the person cool down. So as the alcohol evaporates, what's the value of Q for the alcohol, and what's the algebraic sign of the value of Q for the person's skin? Well, the alcohol evaporates, so you're going from liquid to gas, so Q there is going to be positive. That's an endothermic process, vaporization. And so because the heat that went into the alcohol came from the person's skin, Q would be negative for the person's skin. Okay, so the correct answer there would be B. Which of these processes is endothermic? Take a look at these. You have liquid to gas, liquid to solid, gas to liquid. Well, if you remember, solid to liquid to gas, that's an endothermic process, right? Or you can go solid to gas directly, that's also endothermic. But the opposite of these would be exothermic. So if you're going liquid to gas, yes, that's endothermic. Liquid to solid, that's the opposite. So that's going to be exothermic. That's the opposite of melting. And gas to liquid, that's the opposite of vaporization. That's condensation. That would be exothermic. So this is exothermic, and this is exothermic. Okay. Why is steam more dangerous than boiling water? Well, let's calculate Q for converting 1 mole of steam at 100 degrees, that's water vapor, at 100 degrees to liquid water at body temperature. Body temperature is 37 degrees. So what's going to happen, let's say, if you expose yourself to steam? Well, water vapor at 100 degrees is going to cool down, is going to condense into liquid water, which is also at 100 degrees. So it's going to be from steam to boiling water, and then your boiling water at 100 degrees Celsius is going to cool down eventually to your body temperature, which is 37 degrees Celsius. Okay, so this has a Q, and that has a Q. So the Q for the first one is going to be what? Condensation, right? So negative delta H of vaporization. And Q for this one would be C delta T. Okay, that's just, for the second one, you'll notice it's just a temperature change. No phase change involved there, and no chemical change. And you're given here the delta H vaporization of water. You can look it up. It's 40.7. Specific heat of water, you should know by now, is 4.18 joules per gram per degree Celsius. Okay, so let's say we have 1 mole of water. So 1 mole of H2O gas times the delta H vaporization is negative 40.7 kilojoules, okay, per mole of H2O. So that's Q for step 1 right here. Q for the condensation, that's going to be negative 40.7 kilojoules. What's Q for step 2? For the boiling water to drop down to body temperature, how much heat will it release? Well, let's see. Question number for step 2, Q is equal to C delta T. Heat capacity of water is the mass of water, which is 1 mole. So you change that to grams. 1 mole of water is 18.02 grams. Okay, so this is the mass of the water. Specific heat of water is 4.18 joules per gram Kelvin. And our delta T, what's our delta T? We went from 100 to 37, so that's going to be 37 minus 100 degrees Celsius, or Kelvin, since we're dealing with temperature changes. So Kelvin cancels out, gram cancels out, mole cancels out. Let's see what that number is. 18.02 times 4.18 times parenthesis 37 minus 100, close parenthesis. So that's negative, this is negative 63 over here. That's a temperature drop, so it's going to be releasing heat. That's equal to minus 0.4745. 3 sig, 2 sig figs, so minus 4,700 joules. So that's minus 4.7 kilojoules. Okay? So, your water, as it cools from water vapor at 100 degrees down to liquid water at 37 degrees, is going to release 40.7 kilojoules as it condenses, and then as it cools down from 100 degrees Celsius to 37 degrees, it releases 4.7. Notice that if you look at these numbers, okay, oops, what happened here? If you look at these numbers, compare 40.7 to 4.7, 40.7 versus 4.7. That's about 8.7. Okay, so it's almost 9 times. The condensation of steam to boiling water generates 9 times as much energy as the water just cooling down from boiling to body temperature. That is why if you want to sterilize something, for example, it's better to expose it to steam than just to dip it in boiling water. Okay?